Okay, so we were looking at Lagrange multipliers. Yesterday we looked at an interesting aspect of the Lagrange multipliers, namely the graphical interpretation or the graphical visualization of the Lagrange multipliers, Lagrange multiplier method. In the first few minutes I will reiterate that point and then we will go on to look at a mathematical proof of the Lagrange multiplier method, the economic significance of the multipliers, and what are the second order necessary and sufficient conditions to establish whether the stationary point is a maximum or a minimum or an extremum, and we will wind up with some examples where we look at the second order necessary and sufficient conditions and try to figure out whether the optimum is indeed a maximum or a minimum or inflection point. So if you look at the just a recap on the graphical illustration, the graphical interpretation. So for a two variable problem, this is x1 and x2. Yesterday we drew a constraint like this. This was like, I mean, x1 x2 square is 48 or something. Then so we drew y is equal to c1, y is equal to c2, and so on. Y is equal to 4x1 plus 3x2. Okay, so these are all constant y lines. So this delta y will be in this. Okay, so this is phi equal to 0, phi equal to, so this is a line, this is a curve corresponding to phi equal to 0, therefore this will represent del phi. So we are saying that del y minus lambda del phi equal to 0. Yesterday there was a point whether suppose we move this y is equal to constant into this, any problem Vinay? Suppose there was a question like whether if we move the y is equal to constant line into this curve, what happens? No, I think Abhishek was trying to say no, it will satisfy the constraint. No, it won't satisfy the constraint. Maybe there will be some more point. See, the constraint will be satisfied only if the point is on this curve. Okay, so if you go inside, it does not mean that all the points, any point here will satisfy the constraint. No, it is x1 x2 square equal to 48. Two other points may be, but I am not, but we cannot declare that the whole region, once you cross to the right of the tangent, the whole region becomes a feasible solution. Are you getting the point? However, whatever we discussed was partly right. When you get into the, when you cross that point where you get the actual solution, there may be additional points which satisfy the constraint, but which will definitely have a cost which is more than this, because y is equal to constant is increasing in this direction. I think let us close the discussion on this. Now a quick proof. So the important point to remember is del y and del phi, the two vectors are collinear. Lambda, the introduction of lambda is a mathematical necessity because the magnitudes of del y and del phi need not be the same. So you can have, some books will say del y plus lambda del phi equal to 0, some people will say del y minus, after all lambda is only a scalar, and then please remember that finally the point must be on the constraint. Therefore lambda y minus lambda del phi alone is not sufficient to solve the equations, in conjunction with del phi is equal to 0. Right, a quick proof. Let us consider a I mean this max or min y, maximize or minimize y of x1 x2 subject to phi x1 x2 equal to 0. Okay, this is a standard formulation of a two variable one constraint optimization problem. Okay, so we are seeking a solution to this. Now if you we want to write out an expression for the differential d of phi, the d of phi can be written as fine. When you are seeking a solution to the optimization problem, the constraint has to be necessarily satisfied. Is any d of phi allowed? D of phi has to be necessarily 0, okay. So, therefore okay, any problem Vikram? Okay, therefore I am just doing some algebraic manipulation, that is all. Huh? So, we got an expression for dx1, let us keep it. Now, let us start working on dy, right. Shall I erase this? Similarly, dy can be written as okay. Now, it is possible for me to substitute for dx1 in expression 7 from equation 6, correct. I come again, it is possible for me to substitute for dx1 in equation 7 from the expression I have obtained in equation 6. Therefore, minus rho phi by divided by plus okay. Now, you can substitute for dx1 from equation 6 and you can get this. Now, I say I will look at this and I say, let us say lambda equal to minus I am not violating anything, right, I can define. So India is a free country, so you can define whatever you want. So let us define lambda equal to, now substituting for lambda, so this should be 8. If you are seeking a solution to the optimization problem regardless of the value of delta x1 and delta x2, that means you have a point which could be a1 a2 or whatever. From a1 a2 you are changing that point by delta x1 and delta x2. So regardless of the value of delta x1 and delta x2, if you are seeking the optimum, dy has to be necessarily equal to 0. What? Where?
Plus lambda.
I have defined. Then we will cut the minus. Okay, does not matter, it is up to us. But anyway, we should not make mistakes on the board, right. What is he saying? Yeah, so if you are seeking an optimum, therefore the term within the brackets has to be 0. There is no point in making dx to 0, that is very silly argument, right. Therefore from the definition of lambda, dy by dx1 minus lambda dou phi by dou x1 equal to 0, right. From the definition of lambda, therefore del y minus lambda del phi equal to 0 for the 2 variable 1 constraint problem. You will get additional equations if you have more variables and more constraints. This is what we also try to interpret graphically, okay, outside of all this plus plus plus. Anyway, so equations 11 to 13 constitute a set of n plus m equations. If you have a n variable m constraint optimization problem where m equality constraints are there, this can be solved and simultaneously to get the values of x1 to xn and lambda 1 to lambda m. This is a mathematical proof of the Lagrange multiplier method. Is that okay? So what we are trying to say is, if you have a constraint phi equal to 0 and you are trying to move from the constraint d phi and you make the d phi equal to 0 and then get an expression for the differential of dy and make it 0, which means you are essentially trying to maximize y or minimize y subject to the condition that phi is equal to 0. So mathematically this making d phi is equal to 0 and dy equal to 0 is analogous to solving the set of equations which turn out to be like this. Therefore this is essentially, if you are solving this, you are essentially solving that, alright, fine. So let us look at the economic significance of the multipliers. So, lambda this plus indicates at the optimal point, right. Vectorial form I can write dy by dx1 I plus I can actually multiply by what does it give you? What does it give you? dy dx1 I dxi plus dy dx2, basically it gives you okay. I just changed the inverted triangle to the normal triangle, okay. Therefore, lambda gives the ratio of the change in the objective function to the change in the constraint. This is also called, so this is actually the sensitivity coefficient. Okay. In operations research, it is also called the shadow price. What is the meaning of the shadow price? What is the meaning of the shadow price? Chalk piece. Okay, let us consider a problem. So there is a company which is making furniture. He is very much worried about the chalk piece. Let it be there, no. The soldier should have some blood, right? Okay, so what is this? So what is the shadow price? Let's look at a furniture company which makes only two types of products, table and chair. Okay, so certain amount of wood is required for making one chair, certain amount of wood is required for making one table, certain amount of labor is required for making the chair, certain amount of labor is required for making the table. The cost price of the chair will be smaller compared to the cost price of the table. Therefore, the profit will be some C1 x1 into C2 x2, right, where C1 is the so C1 is basically the profit per chair and C2 is the profit per table, right. You want to maximize the profit subject to the condition that there is a finite amount of labor and there is a finite amount of material available. So this Lagrange multiplier basically talks about, so in this problem for the furniture problem under consideration, so the two constraints are you have the constraints on the time available, the labor and the material, and there is a profit which is y. So if more wood is made available to the furniture company or if more labor is available to the furniture company, how will the objective function change? So it is a shadow price. So if you pump in more resources, what will be the profit? It is a shadow because it is not done yet. If you put in those resources according to all these formulations you have, it should result in so much change in the profit. That is why it is called the shadow price. Alright. Now let us go to some trickier mathematical considerations. We have to look at the higher order, second order necessary and sufficient conditions. So test for maxima minima, one variable problem. dy by dx equal to 0, agreed, okay. It's called a saddle or an inflection point. That means you do not know, the second order test is insufficient, or the function is moving very gently over there, okay, which is very good for us. Okay, mathematicians would like to get a global optimum or global, they want precisely a value of the x1 to xn at which y will become maximum or minimum, but this is dreaded by engineers because all the variables, some measurement is associated with them, they are all subjected to errors. So I would love to have an optimum of y which is not very sensitive to the values of x's at the optimum, that is the engineer's requirement. I do not want something going like this because I cannot get that. Reynolds number 3444, temperature 64.6 degrees, and it will not come. So many variations will be, ambient temperature will change, morning to evening it will change, season to monthly it will change, seasonal variation will. So mathematics is only a tool, we should not get carried away, everything cannot be solved, and actually when something is working, so many things are, there are so many imponderables, we do not have control over many things. Therefore we should have some objective function which gives you some breathing space, where the if a value of y is 100, it should be possible for you to get between 95 and 100 for a reasonable range of the variables, then it is fine. So I will say that any of those solutions which gives y 95 and above, it is all right, okay. So the sensitivity is very, very important, all right. Now what about the test for maximum or minimum when more than one variable is encountered, which is invariably the case in optimization, because one variable problem is a simple high school stuff. We cannot reduce all the problems to one variable problem. We also yesterday we burnt our fingers with an example, simple parabola problem where reducing it to one variable problem we did not get the solution. Therefore oftentimes we encounter a multivariable problem, it should be possible for us to come out with test to determine the maxima or minima. Let us consider a two variable problem. Okay, y is a function of x1 x2, we want to minimize y. We are taking a minimum to y or minimum of y, whatever, okay. Let us say that a1 a2 is a point somewhere near the optimum, or is the optimum itself, but we want to test, right. Can you expand y around a1 a2 using Taylor series? It is possible for us, you can expand y of x1 x2 around a1 a2 using a Taylor series. This will be equal to plus, what is that? One by 2 factorial into x1 minus whole square plus plus higher order terms. Let us leave the higher order terms, assuming the higher order terms do not contribute much. Okay. So, we should start examining what are the, how do we establish the test of, how do we come up with the procedure which lets us determine whether that A1 A2 is really minimum or not. So, what is the first step? If A1 A2 has to be a solution, dy by dx1 must be equal to dy by dx2 at A1 A2, correct? So, first order, because otherwise you can simply change, if dy by dx is a large value, you can simply add, you can simply move the point from A1 A2 some nearby point and then increase the function. If you increase the function beyond this A1 A2 plus, that means already or you can decrease the function depending on whether you are seeking a maximum or minimum. Are you getting the point? Therefore, A1 A2 will no longer be a solution to the problem. Therefore, first order conditions becoming, the first derivative becoming 0 is a mandatory requirement. Okay, this is the first derivative is stationary. It is A R Y, right? E R Y is something else. E R Y is paper and pencil. Okay. Unfortunately, Microsoft Word will not correct it because both are acceptable spelling. It has not become intelligent enough to figure out the context, right? I erased it anyway. So, what is the story now? Higher order terms are neglected, first derivative becomes 0, therefore, the second order terms have to be positive or negative or 0, what is it? If A1 A2 has to be a solution, if you move from A1 A2, any perturbation in A1 A2 will result in a value of y which is more than y at A1 A2. Therefore, it is enough for us to prove that the second order terms result in a positive quantity. I am seeking a minimum only. For a minimum, correct. For a minimum, any perturbation in A1 A2, any perturbation in x1 x2 around A1 A2 will result in a value of y which is more than the value of y at A1 A2. Therefore, y at A1 A2 is indeed the minimum, right. In order to prove that, the second order terms must be, you have to prove that the second order terms or find out conditions when those second order terms together will become positive. Is that okay? Now, therefore, now in order to have in order to make the working easier, I will introduce some notation. A1 A double 1 is dou squared y, A22 A12 the order of the differentiation does not matter. So dou squared y dou x1 dou x2 is the same as dou squared y dou x2 dou x1. Okay. So can you look at the second order terms now? So shall we start with a11 plus 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 must be greater than 0, right. If this condition is satisfied, you are getting a minimum regardless of the value of delta x1 delta x2, right. The story is clear now. Okay. Now how do we get conditions for this? A very crude way is keep on changing delta x1 delta x2 and find this out. I mean but that is very unimaginative, right. You keep changing delta x1 and delta x2 and find out what happens to this. You take 20 values of delta x1 20 values of delta x2, write a small program. Okay, you did it for delta x1 delta x2, suppose you have got for 20 variables 100 variables 200 variables. So there should be something which is mathematically more precise or which will help you get this. Now can you tell me, can you do some mathematical manipulation of this? Up to this it is clear?
Find out x1 by solving a quadratic equations.
Oh, how do you do that?
Take x squared, so the form x squared plus ax plus c equal to c.
No, regardless of the value of delta x1 and delta x2, in fact you know that it is the coefficients a11 a12, it will be these coefficients which ultimately decide the fate of this expression, right. Divided by delta, fine, you start doing, I am going to work out, you start, now establish the condition. I have told you that this is the starting point, there are many ways of doing it, please start doing. Yeah, you can rearrange that 4 and other things can, the 4 is a problem, no, that is why I took this 2 out and I did something, I already multiplied, right. No, I should get a 2 here, right. Yeah, it is okay. Yeah, it is a 2 there, sorry, I mean it is so obvious that I missed the 2. Okay, what do you do now? Yeah, what did you do? Yeah, discriminant, yeah, that condition can be satisfied, but I will work it out. So to save time, what I did was can you write like this, a11 into delta x1 plus a12 delta x2 whole square plus is that okay? No, the a11 will be common for everything, just tell me if it is okay. The a11 will be common for everything. Correct. What I have done now is this will be a11 into delta x1 square, okay, plus 2 delta x1 delta x2 a12 by a11. So the first two terms you will get an additional square term which is a12 by a11 square delta x2, but I put the square minus term here which will cancel, right. So this will be plus a22 by a11 delta x2 square which is coming here, and I am subtracting this again, A12 by A11 square delta x2 square, right. So adding and subtracting. This is a very roundabout way of doing, but that is all right. So now let z1 be delta x1 plus a1 and z2 equal to delta x2. Okay. Therefore, the resulting expression is a11 z1 squared plus, can you tell me, what happened, a22 minus, yeah, can you complete it? A12 square by a11 must be greater than 0. I did not do any magic, I just did algebraic manipulation, that is it. Of course, when I am very liberally multiplying and dividing by a11, the intrinsic assumption is a11 is not equal to 0. If a11 is 0, we have to go home, we have to pack. That is inflection point. Already a11 if is 0 means where there is no scope for us to play, that should not be 0. Okay. Even for a single variable, if a11, that is d squared by dx squared equal to 0, we are in trouble. Now, if for all values of z1 and z2 this has to be true, individually the terms have to be positive. Do not try to find out combinations wherein for some arbit value of z1 and arbit value of z2 this combination will be such that one is positive, one that will not work. For any value of z1 and z2, if the left hand side has to be greater than 0, what a11 and the term within the brackets have to be both greater than 0. Okay. Therefore, for this to be true, for any z1 and z2, a11 must be greater than 0 and a22 okay. Therefore, if D is the matrix of is also equal to if D is greater than 0 and a11 is greater than 0, then Y is a minimum. Okay. So, the D happens to be the determinant of the matrix of partial derivatives. I come again, D happens to be the determinant of the matrix containing the partial derivatives, partial derivatives of second order. Therefore, if you have the Hessian matrix which is defined by if the determinant is greater than 0 and A11 is greater than 0, H is called a positive definite matrix. Okay. So, if H is positive definite, Y is a minimum. If H is negative definite, Y is a maximum. That is A11 less than 0, D greater than 0. If H is indefinite, Y is a saddle point. That means it is an inflection point, we do not know. Immediately expect a question, what happens if D equal to 0?
Singular.
If D equal to 0, then it is a degenerate critical point, the Hessian test is inconclusive. So, very rarely you can set up mathematical equations which will lead to D equal to 0, but in most engineering problems this will not happen. Okay. In fact, for most engineering problems, without doing the test of the Hessian matrix, you will be in a position to decide whether the resulting optimum is a maximum or minimum. However, to be threateningly formal and that to be in order to be clinically correct, you can go for the testing with the Hessian matrix and be sure that the final extremum you obtain is really a minimum or a maximum. There is one more way of looking at it. That is, you have the Hessian matrix of the partial derivatives the second order. If you find the eigenvalues of the Hessian matrix, if all the eigenvalues are positive, then it is a positive definite matrix. If all the eigenvalues are negative, it is a negative definite matrix. If some values are greater than 0 and some values are less than 0, it is indefinite. So, it is possible. So, once you evaluate, for example, the area of the cylindrical storage tank 2 pi r squared plus 2 pi r h. So, dou A by dou r will be 4 pi r plus 2 pi, dou squared A by dou r square will be 4 pi. So, the first term will be 4 pi. You can substitute each of these terms, then you can multiply and take it minus lambda of I, where I is the identity matrix, evaluate the lambda and then find out whether the eigenvalues are positive or negative or some are positive or some are negative, or you just see whether A11 is greater than 0, A1 and A11 is less than 0 and take this determinant and figure out whether it is a maximum or minimum. Now, it may look hazy or nebulous. So, in the next class, whatever problems we have considered, one or out of those 3 or 4 problems we have solved thus far, we will take 1 or 2 and establish that whatever we obtain was indeed a minimum or maximum. For example, the cylindrical storage problem, you could convert it to a one variable problem and then we mathematically establish that it is a minimum. Now, treating it as a 2 variable problem, if you are able to establish that it is still okay, then the results are self consistent or they are all right, fine. Okay. So, if you want more, then you will have to read upon some advanced mathematics books. Kreisig, for example, in Kreisig lot of discussion is there about Hessian matrix and all that. So, the Hessian matrix is a matrix of partial derivatives. If you take the determinant and find, and determinant has to be greater than 0. Okay, if determinant less than 0, it is a saddle point. Determinant has to be greater than 0. If determinant is equal to 0, which will never happen, if determinant is equal to 0, then this test is inconclusive. So, once you get the determinant greater than 0, then look for A11. If A11 is less than 0, it is a max. If A1 is greater than 0, it is a minimum. Okay. So, we will stop.